All right, hello. We are group final project C++, and for our project, we decided to take a data set that represented the roadmap of California and analyze some of or extract some data from it. So our goals for this project were to first, well, in general, to analyze the roadmap of or the roads of California to see how we can better travel through those state, some efficiency purposes, and what else was there? Oh yeah, that's it. And then in specific goals, we aim to implement two different algorithms and a traversal. The traversal was the BFS, breadth first search algorithm or traversal, and then Brandeis algorithm and the Eulerian or Eulerian cycle identification. And then Vinny, if you could make that, then we outputted our data through a little UI interface. Yep, and then you could just return any one of those just to show, and then I'll let Sean go into detail about the BFS.
Yeah, so our goals for the BFS were pretty simple. I mean, we just wanted to implement similar BFS to what was taught to us in class. So not just traverse the nodes, but also store the edges as being discovery, cross, or unexplored. And then we also wanted to store within it like the distances between the node from the start point as well as predecessors. And then I think we're gonna have Vinny talk about our goals for the graph structure and the cycle identification.
Yeah. So let me just make again so I can show off the Eulerian circuits. The other part of our goals was to see whether our graph has an Eulerian is an Eulerian circuit or has an Eulerian path. And what we learned throughout the process of this project was that it's not that simple really to just like find an Eulerian path. There's a lot of specifications. So what we ended up making was a method that will determine whether or not the given data set has an Eulerian path or circuit or neither. So if we run, you can pick a starting node. I just usually pick 0. It's not that important. And then you see it terminates with an exception because the graph isn't Eulerian. So that's just an example of it. In our test, we go into more detail to test with graphs that have circuits and paths, and it returns the path that was found. So that's what we did with the circuits, and we're pretty happy because that function by itself is very versatile. Like we can put it with any graph whatsoever.
Andrew, you can go ahead.
Okay, so next we tried to implement Brandeis algorithm for betweenness centrality. So going into this, I mean, it was kind of complex because none of us really knew even what that was. So what it came down to was kind of reading the paper that explained the algorithm and then kind of following the pseudocode. And it was really important to be able to read deep into the actual paper to be able to understand what was going on in order to debug. So Vinny, if you'll go to Brandeis algorithm in the graph.cc, thank you. So essentially, like the main important design decision that was made here was that I actually added a helper function to graph.cc and graph.h for getting the neighbors, like directly returning the neighbors for any vertex in the graph. So that way we didn't have to loop through all the edges or all the nodes each time to speed up the runtime. And yeah, so as far as the output went, or actually let's talk about the testing first. So as far as the testing went, there were kind of two main cases that we were concerned with. So it was a little bit hard to tell, as you can see in the output there. Like it was a little bit hard to manually calculate values and what they're supposed to be. So we made a smaller graph that is stick shaped. So it'd be a lot easier to manually determine the correct values for each node. And then we also wanted to consider the main edge case that of a complete graph in which no nodes are part of any shortest path between other pairs of nodes. So then they should all come back 0, which if you run the tests will confirm that is indeed the case. So kind of segueing away though, if we talk about the actual results themselves while he makes the tests, we found it interesting that there were so many that a lot of the nodes were on a lot of the shortest paths and a lot of them weren't on any. So that kind of serves to indicate that a lot of nodes and paths are kind of not necessary for traversing from one area of the state to another, for instance, which makes sense because I mean, logically there would be like highways and kind of main arteries to traverse. So it was interesting seeing that reflected in our results.
Vinny, you want to talk about the graph development?
Yeah, so our data set was taken from, oh gosh, Stanford, right? Stanford has a lot of databases for graphs such as this, and this is as I'm scrolling through, this is what it looks like. It's just from node ID to node ID. And what I did is we took this data set, and if I go up in the graph.cc in our constructor, we take a file name in, and we do some file reading to separate the data into nodes. And with that data, then we proceed to start inserting it as vertices and as edges. And within each insert vertex and insert edge, we're checking to make sure that there's no duplicates going in, and to make sure that's most efficient. It's pretty simple graph interface with adjacency lists and such. And we're pretty confident that this is as standard as it can get. We also have for other algorithms that we use, such as in the Eulerian circuits, we had to use remove edges and remove vertex, which are again very similar methods of how you would expect to solve those problems. And yeah, I think I'll pass it to Matt to talk about Eulerian circuits.
Sure. So one of our goals was to develop an algorithm to identify cycles within a graph, and we did this by Benny. If you want to hop over to the graph. Yep. So first thing we had to do was, in order for this algorithm to work, the graph has to be an Eulerian graph. And so we wrote a helper function to help us identify that. And then while we did this, we were testing on smaller graphs in our larger data set, and we found out that our larger data set is not cannot be represented in an Eulerian graph. So in order to test that we properly implemented the algorithm, we made a bunch of smaller graphs and then tested those through the catch 2. And then regarding design choices, could you hop over to the graph.cc one more time? And so we decided to, in our function, we decided to first check if the graph pass was Eulerian, and if it wasn't, we couldn't really analyze anything about it. And then otherwise we decided, or we would figure out whether or not it was an Eulerian cycle or an Eulerian path, and to continue from there. And then I'll pass it on to Sean to talk about the breadth first search.
Yeah, Vinny, you want to just go to BFS? Yeah, so our BFS was pretty standard, similar to the pseudocode that we were given in the lectures for this class. But the hardest thing, and the thing that was like the biggest design choice, was I guess the way we wanted to store the way we labeled the edges. So we did that through a 2D vector, where 0 was unexplored, 1 was a discovery edge, and then 2 represented a cross edge. But other than that, it was pretty much a simple BFS where we just kind of went through each node. If you guys want to start talking about our conclusion here.
Yeah, so Andrew already talked about what we learned from from the between us centrality about, looking at the roadmap of California, and with the Eulerian cycles, it's a bit naive, and we didn't realize that if you take every road in California, you're not going to get a Eulerian circuit. But we have learned from that, more just about how Eulerian circuits work in general. And I think the next step for us would be to format it so we could just like specify, I guess, the size of the Eulerian circuit. That this stuff gets beyond what we're probably capable of at the moment, but doing stuff such as that. And also, just to be clear, like, we have gathered a lot of data with all of this, with the breadth first search, we are able to find the shortest path to nodes. We're able to find nodes with most and least connections. So we've made the means to collect a lot of data. So the next step definitely for us would be to find out, what node has the most amount of connections or the least amount of connections. And like with that data, we know, information about travel in California. So there's a lot to go off of with the data that we've collected, which I think all of us are really optimistic about.
I think that's all we got. So thank you for looking at this video, and have a great rest of your semesters.